Welcome to this explainer, where we are going to crack the famous candies algorithm challenge together. You know, if you've ever stared at an array of numbers, just wondering how on earth to optimize a solution without writing a completely tangled mess of code, well, you are definitely in the right place. Today, we're going to approach this coding problem like a detective, piecing together a brilliant deduction step by step.
Okay, so here's our roadmap for today. We'll start with number 1, distribution rules and patterns. Then move on to 2, the complex two-pass strategy. And finally, number 3, efficiency and conclusion.
All right, section 1, distribution rules and patterns. First up, we really need to gather our clues by clearly understanding the strict boundaries of the universe we're operating in.
Imagine you're teaching a class of kids, all sitting in a row, and each one has a specific performance rating. The core tension here, it's basically neighborly jealousy. Our first rule is that every single child absolutely needs at least one candy. Nobody gets left out entirely. But the second rule, well, that introduces the friction. A child is going to demand more candy if their rating beats the kids sitting immediately next to them.
So this brilliantly illustrates the simplest possible scenario, uniform ratings. When all the ratings are perfectly equal, say a whole row of 2s, nobody is jealous. Since no kid has a higher rating than their neighbor, we can easily satisfy both rules just by peacefully handing everyone exactly one candy.
But what if the ratings aren't equal? Well, if ratings strictly increase, like 1, 3, 4, 6, 8, we just give each child one more candy than their left side neighbor. Conversely, if they strictly decrease, like going from 7 down to 2, we do the exact same thing, but in reverse. We just check the right side neighbor instead.
Comparing these patterns actually proves something super crucial. Our logic is identical in both scenarios. It's literally just acting in reverse directions. We simply check the neighbor in the direction of the decrease. Lock this idea in your head, because this observation, it's a massive clue for building our final algorithm. Moving into section 2, the complex two-pass strategy. Now that we've completely mastered those simple patterns of strictly increasing or strictly decreasing arrays, it is time to face the complex case.
In the real world, and especially in tricky algorithmic challenges, arrays are rarely so neat. So what happens when ratings are completely random? How do we handle a completely non-uniform distribution? I mean, a child might have a higher rating than both of their neighbors, neither neighbor, or maybe just one. This makes our distribution logic significantly harder to track in our heads.
Here's the real trick. We don't try to solve the whole puzzle all at once. We start everyone off with a baseline of just one candy. Take a look at this array of ratings. 4, 3, 2, 4, 5, 1. Giving them all a single candy immediately satisfies our very first rule. Now we just have to deal with the peaks and valleys.
Rather than getting tangled up in a massive, ugly web of nested conditions, we're going to use a surprisingly counterintuitive strategy. We're going to separate our logic into 2 distinct passes. Step 1, we'll sweep from left to right to handle only the increasing relationships. Then step 2, we'll sweep right to left to handle the decreasing ones. Let's actually see this in action.
Let's see how this builds out step by step. We start our first pass at index 1, simply because the child at index 0 doesn't even have a left neighbor. Our rating here is 3. We compare it to the left. Is 3 greater than 4? Nope, it's not.
So, moving right to index 2, we check the rating of 2 against that left neighbor's rating of 3. 2 is obviously not greater than 3, so again, we just move on without adding any candy. Our candies array stays at a baseline of all 1s so far.
Now, notice how the candy count mechanically jumps up right here. At index 3, we have a rating of 4. We check the left neighbor. Is 4 greater than 2? Yes, it is. So we grab the left neighbor's candy count, which is just 1, and we add 1. This child now gets 2 candies. We keep moving to the next index, which has a rating of 5. Is 5 greater than 4? Absolutely. So the candy count jumps up again. We take the left neighbor's 2 candies, add 1, and this child proudly gets 3 candies. See, we're perfectly satisfying all those left side increasing conditions as we sweep through.
Finally, we reach the very last index, which has a rating of 1. 1 is definitely not greater than 5, so no change is made there. And with that, reaching the very end of the array, our left-to-right sweep is completely finished. But hold on, we are only halfway done because we haven't checked any right-side neighbors yet.
Now we're going to intentionally slow things down and reverse course for our second pass. We start from the second to last child to compare them against their right-side neighbors. Our pointer is at rating 5. Is 5 greater than its right neighbor, 1? Yes. But notice, this child already has 3 candies. That's already more than the right neighbor's 1 candy, so we don't need to change a thing here.
We slide over to the left. Now the pointer is at rating 4. We compare it to the right neighbor's rating of 5. Since 4 isn't greater than 5, no adjustment is needed at all. Remember, the rule only cares if the rating is strictly higher.
Sliding left once again, we hit a rating of 2. We check the right neighbor, which is 4. Similarly, 2 isn't greater than 4, so this candy distribution remains completely untouched. Our current array is holding up really well.
But wait, here we finally find a violation. At index 1, the rating is 3, which is strictly higher than the right side rating of 2. Now currently this child only has 1 candy, so we confidently bump their candy count up to 2, ensuring they have exactly 1 more than their neighbor to the right.
And as we complete the final check at index 0, where the rating of 4 beats 3, we bump that candy count up to 3. With our reverse pass officially finished, every single neighborly dispute is resolved. Adding up our final array, 3, 2, 1, 2, 3, 1, gives us our globally correct minimum total of exactly 12 candies. Boom! Solved!
All right, Section 3, Efficiency and Conclusion. We've successfully distributed the candies, but as programmers, we know that just finding a solution isn't the end of the job. Let's lock in our deduction by evaluating exactly why this algorithm is so incredibly powerful.
This entire strategy works flawlessly because it perfectly satisfies what's called the greedy choice property. Notice how we never had to analyze the entire array all at once? By making a locally optimal choice for the current child, literally only ever considering their immediate left or right neighbor during our passes, we basically guarantee a globally optimal minimum total. It is just a beautiful way to reduce a complex problem into very simple, isolated decisions.
Now, let's talk about the raw efficiency. Because we only traverse the array exactly twice, once forward, once backward, our time complexity is an incredibly elegant O of n, scaling perfectly linearly with the number of children. And this is safely matched by an O of n space complexity, which is simply what we need to store our separate candies output array.
Now that you completely understand the mechanics of this 2-pass greedy strategy, I want to leave you with a bit of a challenge. You know the rules, you understand the greedy choice property, and you know exactly how the peaks and valleys dictate the candies. So how might you tweak this logic, maybe by tracking those peaks and valleys on the fly, to squeeze out an O of 1 constant space complexity? Mastering memory optimizations exactly like this is what sets you apart in high-level coding interviews. Think about it, keep experimenting, and hey, thank you so much for joining me on this explainer.